Okay, this is an example of an isobaric process, and an isobaric process means that the pressure inside of the cylinder remains constant during the entire change in volume. And you might want to think about how that would be possible, because if we're going to change the volume, you would think that we would have less pressure if we increase the volume and more pressure if we were decreasing the volume. But remember that we can also affect the thermal energy or the energy content of the gas by adding heat or taking heat out to the surroundings. So if you think about it, if we're going to maintain a constant pressure, kind of how that would happen theoretically is if the volume of the cylinder was increasing and we wanted to maintain constant pressure, we could add heat to the system, thereby changing the internal energy of the gas, rising it to keep that pressure constant. And we would just have to make sure that the rate that this was happening was steady. The other thing is if you were compressing the gas, you might imagine that we would increase the pressure, but one way that we could kind of keep it constant would be to be removing heat from the system at such a rate that we could keep the constant pressure on the inside. That flow of heat or that rate of heat flow would depend upon how fast we'd be changing the volume. So in a problem like this, we know P is the same. So suppose we have a system, monatomic ideal gas, at our pressure that will remain constant. We have an initial temperature of 293 Kelvin, and we're slowly expanding it at a constant pressure from a volume of 1 liter to 2.5 liters. We'd like to find the work done on the environment by the piston as that happens, the change in the internal energy of the gas, and then we'll use the first law of thermodynamics to obtain the thermal energy absorbed by the gas during that process. Okay, so that's what we'll do first. Now if we take a look at all of our formulas that we have so far for the chapter, we have the work done by the gas would be the negative P delta V, or the area underneath a PV diagram. The change in the internal energy is equal to the work plus the heat added or subtracted. PV equals nRT is always available to us, and we also know that the internal energy of the gas is 3/2 nRT at any given state. So we can start out by probably sketching a PV diagram. That would always help. And here we could see that the pressure would remain constant as we expand from 1 liter to 2.5 liters. Now remember, when we're working with pascals, we're going to want to work with units of cubic meters. So we'd have to change our volumes here from 1 liter to 1 times 10 to the minus third liters, and 2.5 liters to 2.5 times 10 to the minus third cubic meters. So if we just calculate from the area underneath this graph, or from our formula, then we'd find that we'd get 300 joules, negative 300 joules of work done on the gas, which means that on the environment there would be positive 300 joules of work done. Okay, so we're extracting work from the gas. The second question asked B, find the change in the internal energy of the gas. So if we do that, the change in the internal energy of the gas, we can look at using our formula like this. However, we don't have enough information about how much heat is being added or removed given in the question anywhere. We do have an alternate formula for finding the change in the internal energy, and that's the 3/2 nR delta T. They gave us an initial temperature of 293 Kelvin in the problem. We know the moles will stay the same, so we could find the final temperature by using our two-state equation. If you think about it, we could use our ratio like this, knowing that the pressure remains constant, that should drop out. Knowing our moles remain constant, that should drop out. And by simple ratios of volume to temperature, we could find the final temperature by the given information. So doing that, we would get a final temperature of 733 Kelvin. Now if we come back to use our formula, we notice that we don't know the number of moles. We know they remain constant, but we did not know how many moles we started with. And so we could use the single state PV equals nRT formula now to find that. And plugging in what we were given, the initial pressure, the constant pressure of 2 times 10 to the 5th pascals, our initial volume, R, and our initial temperature, we can solve for the moles, 0.0821 moles, and then finally calculate our change in internal energy from that given information. So if we do that and you do the algebra, you come up with delta U of 450 joules. Lastly, if we wanted to find the total amount of thermal energy um, absorbed by the system or added to the system, we could go back to our first law of thermodynamics here and solve for Q, knowing it's equal to the change in internal energy minus the work done on the gas. And if we plug in the answers we found, 450 joules minus negative 300 joules, we would find out that there had to be 750 joules of thermal energy added to the system to maintain that constant pressure during that process. And that's it.